I think it's because of the internet connection from my side. It is coming up very slowly. So please be patient.
Okay, because I still cannot see the video.
Hello, everyone, and thank you for joining us today. Welcome to day one of Megger's Virtual Cable Best Practices Seminar. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of each presentation. Today we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. The presenters today will be Sergio Razio and Javier Ruiz-Leva, both being Megger's Cable Fault Location Test and Diagnostic Area Sales Managers. All right, let's go ahead and get started. Thank you so much for joining us today, Javier.
Thank you, Michael, and thanks to everyone for attending today's seminar. Let's start doing a quick review of the agenda for this short 15 minutes presentation. We will go first through the basics for medium voltage cables, and we will analyze what is the VLF test, the parameters, and the goals. Also, we will do exactly the same for the 10 delta and the partial discharge test. We will see what those tests are and what parameters are involved and what are the goals of the three test methods. Well, let's start with the basics for medium voltage cables. We are seeing in the slide the classic single-phase cable in which we have a center conductor that could be of copper or aluminum material. Then we have this inner semicon layer. Next, we have the main insulation of the cable. We will continue with the outer semicon layer. Then next, we will have the neutral concentric shield of the cable. And finally, we will have the jacket or sheet of the cable. Regarding the constructions of the cable, besides the previous one that was the single-phase shielded medium voltage cable, we can have the three-core cable in which we have 3 conductors and each one with its individual shield. And also we have the belted cable. In this case, we have 3 conductors, but we have a common shield. So this is the different cable constructions we can have in medium voltage cables. Regarding the insulation for medium voltage cables, we have the solid dielectric or the polymeric insulation. You can see in the left of the slide the EPR and the XLP insulation, the XLPE insulations. They are maybe the most common insulations that we have nowadays in the medium voltage cables. And in the right, you will see the paper insulated cable. That is also, we can find them also very often in medium voltage installations.
Hello.
In terms of the faults for medium voltage cables, we should distinguish between local issues and global issues. A local issue will be restricted to a portion of the cable insulation or its accessories. And mainly, the local issues are related with poor workmanship or installation products. By the other hand, the global issues are spread along big segments of the cable, and they are related with the aging conditions of the insulation of the cable. So depending on what problem we are dealing with is the test we will choose. For instance, if we are dealing with severe installation or manufacture issues, we can use the VLF test. If we are looking for incipient installations or manufacture issues, we can use the partial discharge test. And if we are looking for all cables and we want to know which cables are the oldest in my population of cables, we can use the 10 delta test. So depending what we are looking for is the test we need to choose. What is the VLF test? Let's start talking of VLF test. The VLF test is fundamentally an AC over voltage test. It's also called AC hypot. And the frequency we use for this AC over voltage test is 0.1 Hertz. In the VLF test, some standards allow to decrease the frequency. Some other standards don't allow to do that, okay? But well, normally we will say that the official frequency for the VLF test is 0.1 Hertz. And the VLF test is pretty much like a pressure test. And we will apply a voltage above operating. The voltage will be prescribed by a standard, for instance, the IEEE 400.2, and we will look for a breakdown. What we want to do during a VLF test is convert in fault the severe issues in the insulation or the accessories of my cable. We use the VLF test as commissioning test or after repair test, and is a go, no go, or pass fail test. So we will have a limited diagnostic information during the VLF test. The parameters involved in the VLF test are the wave shapes. We have mainly two wave shapes, the sine wave shape that you can see in the graphic in the left, and in the right we have the cosine rectangular wave shapes. Of course, both technologies, both wave shapes have advantage and disadvantage, and maybe we'll go through them in the next slides. The test voltage that we use for the VLF test will be between 2 times U0 and 3 times U0, where U0 is the rated RMS phase to ground voltage. And the test time will be between 30 and 60 minutes if we are using, for instance, the IEEE 400.2. The frequency must be 0.1 Hertz, but in the VLF test we have the option to decrease the frequency. For instance, when we want to test very, very low cable with sinus units. The goals of the VLF test are convert in fault a severe problem in the cable insulation and its accessories during the test time, in comparison with the service fault. So this is very important. And we will do this under controlled environment, and we will avoid, of course, collateral damage. Now let's continue with 10 delta test. What is the 10 delta test? Well, the 10 delta test is a global method of testing cables to provide an estimation of the remaining life expectancy of the insulation. We know that there is a correlation between an increase in 0.1 Hertz 10 delta and a decrease in insulation breakdown voltage at power frequency. So the 10 delta is based on VLF technology. We will use a 0.1 Hertz VLF sine wave shape. We cannot use the cosine rectangular to do a 10 delta test. Must be a 0.1 Hertz VLF sine wave shape. It's a diagnostic tool, so we will have 3 assessment criteria: the mean value of the 10 delta, the delta of the 10 delta, and the standard deviation. And the results can be compared with the tables in the IEEE 400.2. And also is a prescribed test method by the IEEE 400.2 2013. Very important also for the 10 delta test, as we can use, as I said, the VLF sine. We must use the VLF sine, and the frequency must be 0.1 Hertz. We cannot decrease the frequency when we are doing a 10 delta test. We can do that in the VLF test, but we cannot do that when we are doing a 10 delta test. The frequency must be fixed, and it will be 0.1 Hertz. The parameters involved in the 10 delta test is the wave shape. The wave shape must be sine, as I said. The test voltage will apply 3 voltages steps: 0.5 U0, 1 U0, and 1.5 U0. This is according to the IEEE 400.2. The test time will depend on the measurements we took per voltage step. The IEEE recommends took between 8 to 10 measurements per voltage step, so it will take around 15 minutes. And I said in the previous slide, the frequency must be 0.1 hertz. 0.1 hertz. We cannot decrease the frequency when we're doing a 10 delta test. What are the goals of the 10 delta test? Well, detect the aging conditions in the insulation of the cable. For that reason, we will do the 10 delta test in all cables, at least cables that have been in service for 5 years. The goal is to alert to critical aged cables before in-service fault and with up to 1 to 2 years notice. And of course, also to help target worst cables first. Now, let's continue with the third method, that is the partial discharge test. The partial discharge are little electrical sparks, and they eat the insulation of the cable. And generally, a partial discharge test, generally, I will say, is a non-reversible process. We have exceptions for this, okay? For instance, in the paper insulated cables, we have exceptions. But normally, in general, we will say that the partial discharge is a non-reversible process. Therefore, they will initiate the final cable fault. So how we do a partial discharge test? Well, we will apply a high voltage to excite the partial discharge in the cable and its accessories. We can use different wave shapes. For instance, we can use the dampened AC. This is one of the wave shapes we can use. We can use also the cosine rectangular slope. Not all the wave shape, only the change of polarity is the slope when the change of polarity happens in the wave shape cosine rectangular. And also we can use the sine 0.1 hertz VLF wave shape, okay? We will measure the partial discharge activity in the cable. We want to measure what is the level of the PD activity in my cable, but also I want to localize the PD activity spots in my cable. As we can see in the graphic at the bottom of the slide, we can see that we have a cable of close to 6.5 kilometers, and we can see partial discharge in the phase A up to 20 nanocoulombs at the beginning of the phase A, and in the phase B and C we can see close to 2 kilometers partial discharge in a joint. Okay, so this is the idea of the partial discharge. Not only measure the PD activity, the level of the PD activity, we want also localize the PD activity spots. What parameter we will measure during a partial discharge test? Well, the charge, of course, the amount of charge, the intensity of each dielectric breakdown, and we will typically measure in picocoulombs. It could be also that we'll measure in nanocoulombs, but typically will be picocoulombs. We will measure also the time the signal from the breakdown takes to reach the sensor, and then we will determine the distance to the partial discharge spot. We will measure also the voltage, the applied voltage. We know that there is a dependency of the partial discharge with respect to voltage. For instance, if we start to see PD activity at 0.8 U0 in the partial discharge measurement, and we increase the voltage, then the level of the partial discharge will increase. So for the reason it's important to see the relation between the voltage, the applied voltage, and the level of the PD of the partial discharge. Also very important is the partial discharge inception voltage, that is the voltage when the PD activity starts in the cable, and the partial discharge extinction voltage, that is the voltage when the PD activity stops in the cable. The goals of the partial discharge is to detect improper installation, manufacturer defects, and third-party damage. Nowadays, the partial discharge is mainly used to detect or to see for poor workmanship issues. It will provide an early warning of the incipient faults, and we will have the possibility of remedial repair or replacement action during a scheduled outage. So this is what is the goals of the partial discharge. And now we will continue with the next topic, that is the tan delta, best practices on tan delta, and it will be presented by Sergio Ressa. Michael, if you can pass the control to Sergio, please.
Sure thing. Sergio, are you ready to receive presenter control? Oh, Sergio, we might still have you on mute.
Yes,
There we
I'm
are.
here. Okay.
All right. Wonderful. Presenter control is heading your way.
Show my screen.
Perfect.
There we go. And I think I erased the slide on accident.
Yep, we're okay.
So thank you, Javier. Thank you, Michael. Thank you, everybody, for joining us today, as my colleague has mentioned. So what we're going to do is go into when to use tan delta. Of course, it's typically used on age cables, 5 years and greater, and we also use this to detect aging condition change and dielectric properties of these said cables. So as you can see in this picture here, to my right, this is a cable tray with old cables sit into it, a service stage cable. It's also be used as part of the cable maintenance strategy. It's going to alert you to critically aged cables before in-service fault and up to 1 to 2 years notice. It's also going to be used as part of a cable replacement project, and where this comes into play is that it's going to let you target the worst cables first, and it allow you to have the best and wisest choice of the available money in which, depending on how valued that asset is, where you should spend your money first. Now we'll go into why to use the tan delta. Of course, this is a non-destructive test, and it is very unlikely to fault the cable during or after this test. It's a diagnostic, so it can estimate the health of remaining insulation of an aged cable. And it's also to detect aging conditions and possible unclean accessories as well, albeit either a term or a splice. And then, of course, increase system reliability in the bulk insulation. What can it detect? It provides an overall condition assessment, estimate life lost in the cable insulation, and it can detect presence of water trees, contaminants in insulation moisture, degraded accessories, and oil leakage in PILT cables. If you look here at this picture, this is an example of a water tree in the insulation, and here's your semiconductive layer, your outer semicon, and your conductor, whether it be aluminum or copper. What it cannot detect is it cannot locate discrete problems, only that there is or is not a problem. As stated before by my colleague, this is a global assessment. What specifically the problem is, it cannot detect either. Is it a corroded concentric, a water tree, maybe a dirty term? Problems in the jacket or the lead sheath, poor workmanship, manufacturer defects, global measurement that does not localize. Basically, this is a leakage current measurement. Not basically, but that's part of what it is doing here. Theoretical approach is the simplistic purposes of the circuit represents a cable with a perfect insulation. If you look here, let me get into my animation here. If the cable insulation is perfect, then the resistor in my circuit, sorry, my webinar thing is blocking my words. Other words, and the value of resistance trends to infinite. This will mean that all the current in my circuit is a capacitive current, and then it is 90 degrees shifted to the voltage applied. As voltage here, there's my resistive, there's the infinite, there's angle, excuse me. Sorry. This is the, sorry, somebody's knocking at my door. Tan delta, represented here in this slide. Sorry, I'm going over to the next slide. Wave shape frequency. Sorry, we use a sine wave shape. Test frequency is at 0.1 hertz. Number of tan delta values, 8 to 10 per voltage step. Which voltage levels? Stepwise increase in voltage. So if you look here on the bottom right, step 1 is at half nu aught. Step 2 is at operating, and step 3 is at 1.5. Any questions? Okay, so why we need to use a sinusoidal wave shape. Here's the sinusoidal as you saw earlier. And then the difference is here on the right, the cosine rectangular. We don't have the phase reference between the current and the voltage in this cosine rectangular for the tan delta measurement as opposed to the VLF. And then in a purely capacitive circuit, the current leads the voltage by a 90-degree angle. As applied here, A is the voltage, B is the current, and then this is the time. Going into this, you're always going to use 3 voltage levels. So the 3 criteria are how you assess within the standard. And that's key because you want to be able to have all 3 of these to be in the standard. And also furthermore on that is that different dielectrics, different types of cables will mask other problems. So if you look here, this is 0.5, 1 times, 1.5. This is the mean VLF TD. If you look at our animation, this is the 8 to 10 values on between each step. 8 to 10 values all between each step. And this is the equation. Here's the differential VLF TD, which is the DTD, as per IEEE 400.2. And then it says here, it's tan delta, the behavioral to increase the voltage. Look here, this is the average of those 10. Oh, sorry, I went a little too fast. This is the average between these here, and these here. This is your value for the DTD. And then VLF tan delta time stability for the standard deviation is the difference between each measurement, all 10 in between each step is the standard deviation. As you can see on the scale as we grow up, this standard deviation is higher, and then so on and so forth. The assessment criteria is the measured values of the TD, DTD, and standard deviation are primarily influenced by the conditions of the cable system components. So historical figures, table 4 is the historical figures of merit for condition assessment of service age PE-based installations, e.g. PE, XOPE, and TRXOPE using 0.1 hertz. So this is the table in the 400.2. As you see here on the left is condition assessment, no action required, further study advised, and action required. VLF TD, so this is actually backwards from what we've shown, but this will be the first slide. Mean VLF TD at operating would be less than 4, would be no action required. 4 to 50, further study advised. Greater than 50, action required. This would be our DTD, difference in mean at 0.5 to 1.5. Less than 5, no action. 5 to 80, further study advised. Greater than 80, action required. And then VLF TD time stability would be, of course, standard deviation. Less than 0.1, no action. 0.1 to 0.5, further study advised. And then, of course, greater than 0.5, action required. Assessment criteria. So breaking those each action down, no action required means no indication of severe problem in the short term. The cable system can be returned to service, and the cable system should be retested at some later date, maybe 4 years. Further study advised would be additional information is needed to make an assessment, comparing historical TD results of the tested cable system. This is important because historical would mean that you've done this more than once in an aged circuit, not new, in an aged circuit. An example of this would be maybe a cable run that before had a failure, you added a splice, and so you had the data before the splice, and then you would have it after the splice. Additional diagnostics test, monitored withstand test, visual analysis of circuit components, and then of course action required would be poor insulation condition. The cable system should be considered for replacement for repair immediately. This is voltage dependency of the tan delta. If you look here, this is just like we were discussing a minute ago. This is on time. If you look at our table here, you have the red reference cable, which is new, the yellow, which is slightly service age, the green is moderately service aged at 2 years, moderately service aged at 3, strongly service aged. So if you look here at this scale, voltage dependency of the tan delta of the new and service age medium voltage XLPE power cables. important factor for decision-making process is the tan delta, also called tip-up. So if you look here at this 1.5 times of this aged cable, you can see here how this is dramatic jump up from the new to the moderate to the service age to the slightly. Oh, sorry. And this is where those the values come into play. So there we go. How to interpret results. So this is a report section of the tan delta. This far left representing the tan delta values. This representing the voltages at each step. And then this is representing of the phases in each set. So phase 1, phase 2, phase 3. And if you look, this is a tan delta on good cables. If you look how they trend between the voltage ranges coming up. And then how we're going to interpret results here. So this is the same cable. One is in the rain and one is in the sunny day. So if you look here at the voltage kV is 12.7 here, 19 here, 25.4 here. Excuse me. Phase 1, phase 2, phase 3, this is your tan delta value at each step. And if you look here, 589, 602, 711 represented by this blue phase here in L3. Then you see the same exact cable here on the sunny day now, same voltage range, 12.7, 19, 254. Phase 1, 338, 388, 500 as compared to 589 in the rain. Phase 2, 343, 394, 477 as opposed to 602 in the rain. And then phase 3, 369, 426, 497 as compared to 711 in the rain. So tan delta is a measure of temperature and humidity. It's also a factor in this. How to interpret the results. So if you look here, this is a wet cable. You see phase 1 is green, phase 2 is red, phase 3 is 3. Same scale, tan delta and voltage. Now, if you look where this starts, when the cable is wet, see how initially it starts high here on phase 3, and then as the voltage is applied and increased, you actually see a decrease, letting you know that it is water. So that's what this cable does here under an actual wet. Limitations of tan delta. In order to meet the standard, the frequency, as my colleague mentioned before, must be 0.1 hertz for tan delta. If other frequencies are used other than 0.1 hertz, and we cannot use the tables of the IEEE 400.2 to evaluate the tan delta. Another limitation is the limited length of the cables under test, around 3 kilometers. And then another major factor is when measuring hybrid insulation types on the same circuit, i.e. you have some EPR, some PILC, maybe some of it is XLPE, and you've tied that in. The different insulations will mask the defects depending on what insulations you have in that circuit. And these are the limitations of all tan delta values. And of course, if you're not using the 0.1 hertz and the 3 steps, there's no table to compare to. The tan delta is a scalar quantity dimensionless unit. The measurement is a function of temperature and humidity, as I stated before, and it's the measure of the loss angle, ratio of resistive and capacitive current. As cables age, the insulation of the resistance decreases, the resistive current increases, and the angle increases. Compare this angle to the IEEE 400.2 2013 tables, and you are able to make the proper assessment. Excuse me. What we have here is our product list for VLF sine units with internal tan delta. So here we have a 45 kV unit and a 62 kV unit. All of these units have a built-in standard assessment reporting already in these units. So these units not only have the VLF technology with the sine wave, they also have the built-in tan delta, so no need for an external missile type connection or extra connections to be able to have your tan delta values. And all of the reporting that we just went over is also built into the assessment report. So for the end user, this is great because as you introduce what cable you're at and the voltages you're using, the standard is built in and it'll give you an automatic assessment. So making that an even easier unit to use going forward with your technicians and looking at data. This is a VLF and TD test using a graph to show you how the connections work. So if you look here, here's our box. This is your power cord for this actual unit. Your grounding, which is going to be usually at your single point, whether it be at your transformer or your connection, your switch. And then this is your high voltage lead to your conductor, whether it be NEMA hole, load break, or dead break. And then the return, which is always right outside the termination where it enters out of the termination. And of course, this is your single point. And this very simply is the connections to be able to take these measurements. What we have here is the top of the screen looking down at these units. As you can see, this is your jog wheel. This is how you control, it's your mouse. It's going to allow you to go into all the functions of the actual unit itself. This is your E-stop. Number 2 here is your power. Number 3 is your key interlock for lockout tagout. Green is your power on. Red is your power off. Number 6 is your USB. And then number 7 is your screen, which looks like this. And this is the actual control panel that you'll be looking at. So if you hear it's a VLF Sinus 45 unit, it is a date and time stamp for you so that you never lose that data. It has the standard that you'll be using at this, in this particular is 400.2, 1.5 times. L1 action required. Of course, here's the VLF 10 delta. And this is your jog wheel as you use your mouse. It's telling you the phases that you've already done, that you're grounded, and so on and so forth. This is doing a 10 delta test. This is an actual data sheet. So once the test is done, of course, it's going to give you this automatic IEEE 400.2 standard assessment for you. Excuse me. This here is a report. Actually, let me blow this up. So if you look here at this report, this is a project cable information. So you can enter in your cable type, what it is, 1/aught, 220 mils, location, your start, your end, the voltages you're using, the phase you're on, cable size, so on and so forth. In your notes here, you can add obviously where your connections are, but also remember we were saying that tan delta is a function of temperature and humidity. You can put what the temperature and humidity is here too, so that as you see this data, you'll be able to know, was this actually affecting me? Was it raining on me? So on and so forth. If you look here, it's this graph, just like we were showing earlier, but now it's in the report of this L1 phase. These are your voltage steps. And if you look phase 1, L1, voltage was 14.9, frequency was 0.1, capacitance was 43. Here's your average tan delta at 43.4. Delta TD was 52.9. Standard deviation is 0.71. Average tan delta result. And here it has all 3 of each phase or of each step. And your result, of course, is action required. And the criteria, it even breaks it down to as to what criteria you are going to. And the inspector or user as you like. Here's another look at those same things. So this is the action results as this whole system works. Okay. These are the webinars about VLF TD that we have on the web. So this is the Megger.com webinar, the YouTube, and I'll leave these links up here for a few seconds if you would like to write them down or take pictures of them. But these are additional training.
And we'll also have those in the follow-up email going out tomorrow morning with a copy of these presentations and recording of the webinar. So don't feel too pressured to write these down exactly at this moment.
Thank you, Michael. Appreciate that. Yeah, I should have mentioned that. They will be at the end of the presentation. This is the contact information for me, Sergio Razzo, srazzo@megger.com, USA Sales. I'm officially over the Southeast region, but we are all a team, so we'll help whoever is in need.
All right, and we are good to go.
Okay, thanks, Michael. Let's start talking of PD measurements. The first that we need to, maybe the first answer we need the first question we need to answer is, what is a partial discharge? If you go to Wikipedia, you will find this definition is a partial discharge is a localized dielectric breakdown which does not completely bridge the space between the two conductors of a portion of a solid or fluid electrical insulation under high voltage stress. If you see the drawing we have in the slide, we have two conductors in red, and in between we have the insulation. And inside of the insulation we have an air bubble or a cavity filled with air. So what happens with this device is under high voltage is that the high voltage will build up inside the cavity, and we will have a breakdown, we will have a spark. And every time that happens, the walls that constrain the air bubble or the cavity will be carbonized. So sooner or later, we will have a fault between the two conductors. So this is the definition of a partial discharge. So when we will use partial discharge, when to use partial discharge? Well, we can use partial discharge as commissioning test or after cable repair tests. And the idea or the goal is to find improper installation, manufacturer defects, or third-part damage. Partial discharge is especially good to find poor workmanship issues or manufacturer defects, or also installation problem. For instance, in somebody, if we have if the cable was bent too much, we will have a chance to find that kind of issues with partial discharge. As you can see in these pictures, the guy that fixed the cable in the holder exceed the torque, and for this reason they deformed the insulation of the cable. So for that kind of problems is that partial discharge will help us. So the partial discharge will provide an early warning of incipient faults, and we will have the possibility of remedial repair or replacement action during already scheduled planned outage. So how the partial discharge works? How the partial discharge works? As I mentioned, we have two ways to measure partial discharge: the conventional way and the non-conventional way. In the conventional way, we need to connect in the circuit between the power source and the cable under test a coupling capacitor. So we need to de-energize the cable in order to connect the coupling capacitor and the power source. And in the conventional way, when we use the coupling capacitor, we will work under the IEC 6270. Okay, so only when we work in the conventional way is allowed to speak of picocoulombs. We will see in the next slides that we will measure the partial discharge, and the unit of the partial discharge is the coulomb, and we will measure very small quantities of charge. For this reason, we will measure in picocoulombs, at the best nanocoulombs. Okay, but only in the conventional way we will need to calibrate the circuit. And when we calibrate the circuit, what we do is to put a calibrator at the beginning of the cable. We will inject a PD pulse in the cable, and what will happen is that the energy of the PD pulse we are injected with the calibrator will split in two. The first part of the energy will go back straight to the coupling capacitor, and the second part of the energy will go all its way to the end of the cable, and then will go back to the coupling capacitor. Then during the calibration, we will have two pulses, the first one and the second one. Okay, and this principle is the same that we will use to localize the partial discharge. We have, let's say, an air bubble inside of the insulation of a cable. So we will have the partial discharge. The energy will be split in two. Part of the energy will go straight to the beginning of the cable, to the coupling capacitor, and the second part of the energy will go to the end of the cable, and then will go back to the coupling capacitor. Then, as I said, we will have two pulses, okay? And these pulses will have a difference in time. The difference between the arrival of the first pulse and the arrival of the second pulse. So we will have a difference in time, and we will know the propagation velocity of the partial discharge pulse, so we can localize the PD spot in the cable. So is the way also is the way how we localize the partial discharge spots in the cable. So what we will measure during a PD test? The charge. The charge is very important, the amount of charge, which means the intensity of each dielectric breakdown. And typically we will measure in picocoulombs. Also, we will measure the time, as we saw in the previous slide. The time is very important. The time the signal from the breakdown takes to reach the sensor, meaning the coupling capacitor, and then we can determine the distance. The voltage is also very important because there is a dependency of the partial discharge versus the voltage, which means that if we detect PD activity at 0.8 U0 and we increase the voltage to 1 U0, the level of the partial discharge will increase. So that relation is also important. The other two parameters that are very important is the partial discharge inception voltage, which means the voltage when the PD activity starts in the cable, and the partial discharge extinction voltage. That is the voltage when the PD activity stops in my cable. For that reason, we recommend to increase the voltage step by step to detect or to find the PD IV and the PD EV. We have some guidelines for the partial discharge test. For instance, here we see that for aged cables in this guideline, we have that for instance, for a maintenance partial discharge test, the insulation must be PD-free. So in a maintenance test, we should have not partial discharge in the insulation of the cable. But for instance, in the splices, we can allow up to 1 picocoulomb, okay? Sorry, less than 1,000 picocoulombs. That will be the limit, okay? For aged cable and the splices, we should have less than 1,000 picocoulombs, and the same for the terminations, less than 1,000 picocoulombs. So we have different guidelines, and we can use them to make a decision after we do a partial discharge test. Once we're done with the partial discharge measurement, we will have a complete report, and we can analyze the report in order to make a decision. For instance, in this table, we're seeing that, sorry, this is in Spanish, my apologies, but what we have in the first row is the background noise level, And you can see that almost is the same background noise level for the three phases. But in the phase L3, you can see that we have the partial discharge inception voltage was 19.8 kV, and the partial discharge extinction voltage was 10.4 kV. So by the other hand, in the phase L1 and L2, we didn't find any kind of PD activity. And the other very important parameter is the PD level and maximum voltage. In this case, we applied up to 2 times U0. And you can see that in the phase L3, we get a PD level up to 5,788 picocoulombs. So this is the way we know that in the phase L3 we have partial discharge activity. It's very important that we have a good calibration. That is very important. Sometimes I see some reports in which the calibration was not successful. So this is very important that when we analyze a report of partial discharge, we see the calibration. And also it's very important the location of the PD activity. The location of the PD activity. If you see, we didn't have PD activity in the phase L1 and L2 for the reason we don't have any dots, blue and orange dots in the graphic. But in the phase of 3, you can see that we get a lot of partial discharge at the end of the cable. The cable was 500 meters, so you can see very clear in this graphic that the problem was with the phase of 3, and the problem was at the end. In this case, the level of the partial discharge, as we saw in the previous slide, and we can see right now, was 5,788 picocoulombs, which is above of the guideline we showed in the previous slides. So the guys that made this PD measurement should replace the termination of this cable. So what is important when we are doing a PD measurement? One of most important parts of the PD measurement is ensuring a good connection to the test object, okay? You are seeing one example of the connection of the setup, so the connection of VLF with the coupling capacitor, okay? And it's very important that during the connections, we'll be very careful doing all the connections between the cable under test and our unit, because a faulty connection could cause that we have an increased background noise level, or maybe we should create partial discharge in the circuit. We can put partial discharge in the circuit doing a faulty connection, or maybe we'll create a partial discharge at the near termination. The other problem we can have when we have a faulty connection is that no partial discharge activity will be measured at all, or will not be able to load the test object, okay? So it's important to have a very good connection between the PD equipment and the cable under test. We need to be always sure that we will connect the ground of the equipment on the same point as the return. If you see in this drawing, we have the high voltage lead of my cable connected to the cable under test, but the grounding is connected in this bus bar. And what we need to do when we are doing partial discharge test is that the grounding must be connected at the same point where we connected the high voltage test lead, the return of the high voltage lead, the return. So this is very important to avoid the antenna effect during the measurement. So always try to connect the grounding of your PD equipment in the return, in the point where you are connecting the return of your high voltage cable. Here we're seeing an example of a PD measurement. It was made in a cable with a length of almost 21,000 feet. The insulation was XLPE and the voltage was 35 kV. And you can see here in the horizontal axis, we have the length of the cable is 6.5 kilometers, which means around 21,000 feet. And you can see in the vertical axis the level of the partial discharge detected. And you can see that in the phase A, we have PD activity at the beginning of the cable, and the problem was that we didn't have a PD-free connection. For that reason, it's very important to have a PD-free connection between the cable under test and our high voltage test lead, okay? But in the phase B and C, you can see that at 5,900 feet, we have PD activity in the phase B and C. So when we open the, when we take out the splice, the joint, we saw that the guy that made this splice didn't put the mastic to seal the screw hole, okay? You can see here the screw holes, and sometimes in the connectors you need to put a mastic to seal that holes. They didn't do in this splice, and that was the reason of the partial discharge activity in the measurement. For finish the presentation, I would like to show you some of the PD equipment we have in Megger. The first unit we have is the damped AC or the DAC 30 kV. This unit is only to perform the partial discharge test for 15 kV cables, and it's a unit that reaches up to 30 kV peak. And this is we use the damped AC wave shape to perform the PD test. The next units we have in Megger is the TDS-NT 40 kV and 60 kV. We have two models, and the first one, the TDS-NT 40, is for 15 and 25 kV cables, and the TDS-NT 60 is for 15, 25, and 35 kV cables. In the TDS-NT models, we have two options, two versions. The basic version, for instance, for the TDS-40, will have 2.4 microfarads, and the plus version will have 4.8 microfarads. In the case of the TDS-60, the basic version will have 1 microfarad, and the plus version will have 2 microfarads, which means that if we have more test capacitance, will allow us to test longer cables. So this is the TDS-NT 40 and 60 kV, and we can do the VLF test and also the partial discharge test using the damped AC wave shape. The next unit we have the next unit we have is the VLF Sine 30. It's a sine wave shape technology unit. It's a very small unit. In this case, we can do the VLF test. We can also do the tan delta test, but in this case, we need an external tan delta attachment. We need an external tan delta attachment for the VLF Sine 34. And for the PD test, we will use this coupling capacitor that is our PDS62. The next unit we have is the VLF Sine 45 kV. It's also a this unit also uses a 0.1 Hz sine wave shape. In this case, we can do also the VLF test. We have an internal tan delta, as Sergio mentioned. We have an internal tan delta built up in the unit. And if we want to do the partial discharge test, we need our PDS62 also. And next we have the TDM Sine 4540 kV unit that is really a very interesting unit because we will have everything we need for VLF, tan delta, and partial discharge. The TDM is a VLF Sine 45, but we can put a booster, and with the booster we will have also the cosine rectangular wave shape to do the VLF test. And with the booster we will have access to the cosine rectangular wave shape for the VLF test, but also we will have access to the damped AC for the partial discharge test. And of course, as this is a VLF sine wave shape unit, we can use the VLF sine 0.1 Hz wave shape to do the tan delta. So with the TDM Sine 4540 kV, we will have access to all the wave shapes, or the more important wave shapes that we use for the VLF test, for the tan delta, and for the partial discharge test. We can have different options depending on what we are looking for. We can have the TDM 45 with tan delta and VLF only. We can have the TDM 45 with the VLF, the tan delta, and the partial discharge option. We can have the TDM 4540 with the booster only to have the VLF sinus and the VLF cosinus rectangular for the VLF test. And we can have the VLF, the TDM 4540 with the booster, which will allow us to do the VLF with the sinus wave shape, with the cosinus wave shape. We will do the tan delta, and we can do also the partial discharge test with the sinus wave shape, with the damped AC, and with the slope of the cosine rectangular wave shape. So depending on what you are looking for, you can select the options for the TDM Sine 4540 series, and depending on what you're looking for, we can provide it. Okay, so it's very convenient unit. And the last one, the last unit we have is our VLF Sinus 62. This is a sinus VLF, has an internal 10 delta, and also we can use the PDS 62 to do the partial discharge test. So this is the biggest VLF, the biggest sinus VLF we have, and this is our VLF Sinus 62, and is a very nice unit because the cable is integrated in the unit, also the partial discharge, so it's a very convenient unit. And with this, I think that is all what I have for you guys, so I'm ready to have some questions if you have it.
So now it comes to our Q&A session. If you have any questions, please type in the question panels. Our panelist, Lino, will answer your questions.
Hello. Yeah. Good afternoon. Late afternoon to all. Moderator for us this afternoon, Michael was not available, so I'm taking over Michael. Now we are having some. We are now at Q&A session. We have, I think, only one gentleman asking good questions around. His name is Fajar Nugraha. I'm not sure if you all see his question, but I can read out. Some question has been answered by Leno. The first question is, could you explain criteria of acceptance for cable testing for all testing such as insulation, VLF, HV test, and PD test? You know, this is a very general question. If we're going to have a detailed answer, it will take hours. I think Leno have answered quite good directly to Mr. Fanjal. He said that only based on experience. So he had the IR testing is above gigaohm. VLF testing is go no go pass with the recent testing for recommended voltage apply, and duration test of course must refer always to the VLF to the IEEE standard 400.2, and PD testing are PD free and no concentrated PD at any joint or along the cable or termination. Moving to the second question from Fajar as well, he said he asking that on 10 data cable power, which parameter that we must focus. So the answer is based on 10 data evaluation graph, typically recommended VLF TD above 4 times at 10 approximately minus 3, and VLF DTD greater than 5. And also, I didn't see what is that. Greater than 5. Yeah. Sorry, I don't see the menu. Menu is so small. Let me increase the menu. Yeah, the 10 data deviation is greater than 5 value, and TDTS greater than 0.1. I believe this is the standard in IEEE 400.2 in a table 3, so it can be easily guided over there. And again, another question from Fajar, why we use test frequency 0.1 Hertz, on 10 data, if our system is 50 Hertz, is that okay? Of course, that is why we are here today. The VLF 0.1 is international's recommended, and there's good answer from Leno as well. So the small scale device size, you can have the same capability to test through comparable with AC more than 500 times. If you on the additional for that, if you look into the AAA standard 400.2, is also described that using the 0.1 VLF system, ideally is 500 to 50 Hertz time, 1/600 to 60 Hertz time, actually having the lesser charging current. So you can have a smaller device to test the same capacity of the cable. So that is the reason why VLF 0.1 Hertz has been very high accuracy and reliable to test the cable. It has been proven anyway. Don't worry for that. And another question from Fajar, on 10 data cable, length of cable will affect of the result. The answer is the length of cable will affecting you test load capacity. Base recommended is 1 microfarad, about 4 kilometers. So again, additional information for you all, that if you are testing 10 or 20 kilometers cables, using a tangent data, that's again a big challenge for you. You need a very high capacitance tester to test tangent data. Again, dielectric analysis will give you a very confused result because the cable is too long. So that is the reason why our day one seminar today come with the alternative option for you to do a diagnostic using a partial discharge. So that could be an alternative for you along for you to diagnose your cable. All right. So, and Fajar have clarified that he has one of a Megger unit here that is using the VLF Sinus 45. That is unit having internal tangent data, and of course it should not be a problem for him to conduct testing continuously. And what else? And yeah, I think the answer, the question, another question from Fajar as well. He said, I do not but I'm not sure what this question means, but I do not. It is included with internal tangent data. So just check this system with us. Give us a serial number and we can tell you. If you purchase with tangent data, you can just activate the tangent data. That's quite easy, all right? And I have also answered to him to the question as well. So the pre-program VLF TD Test, DTD and TD mains has been pre-programmed, and you can do the testing easily. I think the rest, no other question from others besides Fajar. So should I give you guys another 1 minute? If you have any question, please raise up. Type in the mailbox, tell in the box, or leave your email address to us. We will come back to you with all the technical questions if we are unable to answer you today. But I don't see we have any difficulty here. Any more questions from all of you? Otherwise, and just to remind that we have day 2 webinar tomorrow, same timing. That is more on the cable fault. This webinar is actually especially and dedicated arranged day 1 and day 2 webinars from US colleague that we have this pre-recorded to run the same webinar they had on today and tomorrow, so that to fit our Asia timing and we all can enjoy this webinar. So if there isn't any more question, I think we can close this seminar today. And one thing is all the video will be pre-recorded. I think the organizer Grace will circulate the video to all of you. to all the participant attendees. And also the PPT, we will circulate the PPT. To all participants. If you have any colleague that he want to have our PPT and this recorded video, do share with them, no problem. All right, Grace, over to you to close this webinar then.
Okay, thank you, Patrick. Thank you everyone for attending. So if you have any further questions, please feel free to contact us, any of us. Don't forget, when you leave the webinar, there will be a survey. Please fill in the survey to give us some comments for improvement. So I've just posted the registration link for tomorrow's cable testing webinar. So if you haven't registered yet, please click the link